This is a lecture on molecular shapes. Molecular shapes are really important. They determine chemical reactivity in particular, and that's especially important to us in pharmaceuticals, the medicines we take. As you probably know from biology, a lot of the way our body works is kind of by a lock and key system where molecules that are needed to activate something fit in a specific active site. And so when we're developing medicines, it's critical that we take their shape into account. It turns out that what determines the shape of a molecule, are the valence electrons. Of course, electrons have a negative charge, so they repel each other. So the valence electrons that arrange themselves around the atoms that make up a molecule try to get as far away from each other as possible. The theory that describes this is called VSEPR for short. That stands for valence shell electron pair repulsion theory. And again, it describes, if looking at the central atom, it describes each area of electron density. So that would be either a chemical bond or a lone pair, an electron domain. And then if you arrange the electron domains around a central atom so that they're as far away from each other as possible, you can predict the shape of molecules. So to give you an idea how to count electron domains, let's look at this made-up molecule, for example. So one of the things that's important to remember is that we're looking for regions of electron density. So this, although this is a double bond, it only counts as one domain. So this central atom A has 1, 2, 3, 4 electron domains around it. So don't spend too much time trying to understand any details in this slide. I'm just giving you a preview of what I'll go into more detail about slide by slide. But as you can see, if you imagine yellow is the central atom in each of these figures, the top image has 2 electron domains around the central atom, the next has 3, etc. And if you keep in mind that the electron domains try to get as far away from each other as possible, each of these shapes shows, depending on how many electron domains there are, the shape that that molecule would adopt to keep all of the electron domains as far away from each other as possible. All right, so let's get down to the procedure you need to go through in order to predict a shape. The first thing you need to do is draw a Lewis dot structure. Don't take any shortcuts with that. Just make yourself be somewhat disciplined and go through the steps necessary to get an accurate Lewis dot structure. So if we took a simple example, ammonia, NH3, so if you're just looking at the formula and you don't bother to draw a Lewis structure, you may think ammonia has 3 electron domains. But if you draw a Lewis structure, you realize there's also a lone pair of electrons on the nitrogen, so there are, in fact, 4 electron domains. Alrighty, so to further complicate our lives, there is an electron domain geometry, which looks at every single electron domain around a central atom. And there is also a molecular geometry, which we will be talking about. So you have to go through the electron domain geometry because that is the geometry that sets up the angle and the placement of every atom that is bonded to that central atom. But it so turns out, I want you to imagine taking a picture of ammonia, actually an electron scanning micrograph, but anyway, and then imagine that lone pairs of electrons are not going to show up in your picture. They are there exerting their repelling force and keeping the atoms in the place that they're farthest away from all the repulsions. However, this lone pair is just not going to show up in your little snapshot. So that is the molecular geometry. So again, molecular geometries do not show lone pairs, although they acknowledge that the lone pairs are there and affecting the geometry. Alrighty, this just kind of says in words what I just said verbally. But just to kind of glance, all of these have 4 domains, okay? But the ammonia example that we just talked about has 1 lone pair. Water has 4 domains, okay? But 2 of those domains are lone pairs, all right? And then, of course, if you have CH4, that's methane, there are no lone pairs. So, if there are no lone pairs, the electron domain geometry is identical to the molecular geometry. Okay, so I'll say that one more time. If there are no lone pairs around the central atom, the electron domain geometry is identical to the molecular geometry. However, once you introduce lone pairs around a central atom, the electron domain geometry is different, is not the same as the molecular geometry. So you'll see that more specifically as we move on. And for every lone pair you introduce around the central atom, the molecular geometry changes each time you introduce another lone pair. I'm going to walk you through every possible scenario now of electron domains from 2 domains around the central atom up through 6 domains, which is the most you can have. And then for each domain, if you introduce a lone pair, how it changes the molecular shape. So the easiest one, obviously, if you have 2 electron groups, 2 electron domains around a central atom, it will adopt a linear shape, okay? If these 2 domains around the central atom are trying to get as far away from each possible, linear shape is the best shape. Pay attention to the angles associated with each shape. Those are important to know too. So the angle associated with a linear shape is 180 degrees. I just want to point out here, carbon dioxide is linear, but if you didn't bother to draw a Lewis structure of carbon dioxide, or you might think, you could imagine almost any shape. You might think, okay, maybe it's bent, whatever. But yeah, so make sure you draw the Lewis structure of these. All right, 3 electron groups. If you have 3 electron domains around a central atom, and of course they're trying to get as far away from each other as possible, they will adopt what we describe as a trigonal planar shape. And the angles between the bonds are 120 degrees, and that's because this structure makes a circle. Okay, let's see. Alrighty, so now if you have 3 domains around a central atom, what happens if one of those 3 domains is a lone pair of electrons? Again, that lone pair of electrons acts as an electron domain and forces the bonding atoms into this trigonal planar electron domain position. But imagine taking a snapshot of this, and remember that in your snapshot, lone pairs don't show up. So the molecular shape, that's the shape without looking at the lone pair, is bent. All right. So both of these structures have an electron domain shape or electron domain geometry of trigonal planar. It's only the molecular geometry and molecular shape that is different. 4 domains. Now it starts to get somewhat trickier. A really common mistake made by students when they draw the structure CH4, it's called methane, it's actually natural gas, is they'll tend to draw all of the hydrogens like they're in the same plane, like it's a flat molecule. No. So if you have 4 domains around a central atom, the shape they adopt to get as far away from each other as possible is called a tetrahedral. I always remembered this as a student because it reminds me of a tripod. Photographers have, where they have this device where it has 3 legs that hold it up on the floor, and then there's a long stem coming from the top that they put their camera on. In this case, we put another atom on it. But that's kind of what a tetrahedral shape looks like. The bond angles are kind of weird. They're probably easiest one to forget, 109.5. All right, so we're getting more electron domains, so now there's the chance for more lone pairs. So as I said before, if there are no lone pairs, the electron domain shape is the same as the molecular geometry. So in this case, it's tetrahedral electron domain shape and tetrahedral molecular shape. Once we introduce one lone pair, okay, now keep in mind that these bonds stay where they were depending on that lone pair. So they can't start flattening out or moving just because our picture is not seeing the lone pair. So what we have left, and I'm going to turn that 90 degrees because it's easier for me to see. What we have left with one lone pair and looking at the molecular shape, okay, is something like that. So you imagine your tripod with 3 legs holding it up, but then you're just not seeing this part, okay? We call that a trigonal pyramid, trigonal pyramidal. If we have 2 lone pairs, and that would be like water, okay, which has 2 lone pairs, and then 2 oxygen-hydrogen bonds, that is now, again, if you block out the lone pairs, that is now what we describe as a bent shape. And if you have 3 lone pairs, you only have 2 atoms left, and of course that's linear. Let's walk through an example. Let's say you were asked to predict the geometry. Let's just say you were asked to predict the electron domain geometry and the molecular geometry for phosphorus trichloride. As I said before, step 1 is always to draw a Lewis structure. If you need a refresher on that, the first thing you do is count total valence electrons. Phosphorus is in group 5A, has 5 valence electrons. Chlorine, a halogen, has 7 valence electrons, but there are 3 chlorines. So if you add all those together, you see you have 26 valence electrons. So we start, it's almost always the first atom that goes in the center. So draw single bonds between the central atom and the rest of the atoms, and then give all of the outer atoms an octet of electrons. And at this point, you have, anytime you make an octet, you've used 8 electrons, right? So 8, 16, 24. So you have 2 electrons left to place. Leftover electrons go on the central atom. So this is the correct structure for phosphorus trichloride, and that leaves us with how many domains? 1, 2, 3, 4 domains. So the electron domain shape with 4 domains is a tetrahedral. Okay, but we know the molecular geometry is not going to be called tetrahedral because it has a lone pair. So then you have to remember, so at this point I would sketch out a tetrahedral shape before I made a decision on the molecular shape. So I would do this. All right. And so then cover up the lone pair, and this is kind of like the bottom part of the tripod. So that is trigonal pyramidal shape for molecular shape. Now this one is kind of tricky, and I wish I was there in person to show you a 3-dimensional model. If you have trouble understanding what I'm saying, you might want to Google 3D representation of trigonal bipyramidal shape. So if you have 5 electron domains around a central atom, we call that trigonal bipyramidal. And to envision that shape maybe a little bit better three-dimensionally, here's your central atom, okay? You've got one of your domains going straight up, one going straight down, and then you have three domains spread evenly around the equator of this central atom. So there's one, and make this thicker because it's coming out at you, and then here's a third one, okay? So you can kind of think of these three as a pinwheel spinning around the equator. And these positions are different. That's really important to remember about trigonal bipyramidal too. The axial positions are different, not equivalent to the equatorial positions. And so let's look at the angles, for example. There are a few differences. But the three domains around the equator are kind of, if you take them alone, it's kind of like a trigonal planar structure where the angles are 120 degrees, okay? But if now you look at the axial and it's encountering, or how close it is to an equatorial position, that is 90 degrees. So now it comes into play why the equatorial versus axial, you have to keep in mind these are two different positions. Because if you are an electron pair, a lone pair, I can't get that out, of electrons, and you're repelling. Remember, all your neighbors repel you when you repel them. So you want to get as far away from everybody, all the other valence electrons you can. Where would you rather be? Would you rather be in the axial position or equatorial? Well, hopefully you picked equatorial because you've got 120 degrees between your nearest neighbors. Whereas if you pick axial position, you're only going to be 90 degrees from all of your neighbors. All right, so again, this is just kind of putting into words what I verbally described in case it sinks in a little bit better for you. One other thing I want to point out here is that notice how many total electrons are around the central atom. There are 2, 4, 6, 8, 10. Okay, so rather than an octet, this compound, or this atom, phosphorus, has 10 valence electrons, so it has expanded its octet, which is fine. As you remember, all atoms, all elements that are in period 3 on the periodic table or down farther on the periodic table, so that would be periods 3, 4, 5, 6, and 7, are capable of expanding their octets. And so the trigonal bipyramidal shape will only come into play when you have an element, a central atom, that's capable of expanding its octet. As you can imagine, we can introduce, from 1 up to 4 lone pairs around if there are 5 electron domains. So let's look at them one at a time. And you've got to commit to memory these different shapes. So I think understanding where the shape got its name will help you so you don't just have to blindly memorize. All right, so if we have the trigonal bipyramidal shape and we have 1 lone pair, remember that the lone pair always goes into the equatorial position because there's more space for it there. And what are you left with? It's a little hard to visualize here, but if you turn this structure by 90 degrees, you maybe can recognize where it got its name from better. Okay, so if you imagine you and your friend sitting in the flooring and going up and down, this is a teeter-totter or seesaw. And that's exactly what they called it. Seesaw. All right. And let's go on now to if we have, you can come back to this slide, but I want to show you a larger picture. If we have 2 lone pairs. All right, if we have 2 lone pairs on the trigonal bipyramidal shape, both of them go in an equatorial position, and this one's probably easier to see. So if you take a snapshot of this shape, we call that a T shape. And again, if you turned it 90 degrees, it might be easier for you to see. But that is a T shape for the molecular geometry. Remember that the electron geometries, the name comes only from how many domains. So every single electron geometry, if you have 5 domains, is still trigonal bipyramidal. It's only the molecular geometry name that changes. All right, and finally, which this is kind of odd, if you have 3 lone pairs, of course they occupy all 3 of the equatorial positions, and what you're left with for the molecular shape is linear. So you can get a linear shape starting with a trigonal bipyramidal electron domain shape. Alrighty, the last electron domain shape, the most electron domains you can have around a central atom are 6. Okay, 1, 2, 3, 4, 5, 6. And again, that can only happen with central atoms that can expand their octet. In this case, the central atom has 2, 4, 6, 8, 10, 12 electrons around it. Alrighty, so different from the trigonal bipyramidal, the octahedral geometry, all of the angles are 90 degrees. All of them, regardless of the one that you look at. So all positions are equivalent and you don't have to worry about axial versus equatorial positions. So taking a look at these, and I'm going to add to one of these. I think it'll help you look at it. Most of these molecular geometry names come from essentially connecting the exterior atoms to each other to see what shape they would make. And so I'm not a very good drawer, so this might not help, but in case it does. So you might be able to see that this makes a pyramid. There's one of the sides. Okay, and then let's see. Here's another side, and then there's a back to it, and yet another side over here. Okay, so think of that. That's kind of like a pyramid structure, and there's the same, you can do the same thing to the bottom, okay, to get a pyramid structure. And so the word octahedral, I have a lot of students who say, wait, there are only 6 domains. How are they getting that word octa? It's because if you connect the atoms, so to say, and draw a shape, there are 8 sides. Okay, 4 on top, 4 on the bottom. So 8 is octa. Once you introduce one pair, and then what do we have left? Well, in order to understand the shape they come up with, whoops, that was not good. Okay, I'm going to connect these atoms again. Okay, and maybe you can see that we now have our pyramid. And what this is called is the square pyramid, and it's called square because the base of the pyramid is a square. Okay. If you have 2 lone pairs, again, it doesn't matter where you put the lone pairs in the octahedral because all positions are equivalent. But it's easier to visualize, I think, if you put them straight up, straight down, and then ignore them. And what you have now, you literally have a square left. The remaining 4 atoms are on the same plane, which is why we call this shape square planar. All right, the rest of this PowerPoint are just some kind of nuances, or think of it icing on the cake to better understand these shapes. If you have a lone pair of electrons as one of your domains, and so I'm going to draw these in, and this is probably intuitive, a lone pair of electrons has a stronger repelling force than 2 bonding electrons, okay? And that's because if you imagine 2 electrons between 2 atoms, they're already being shared between those 2 atoms, not quite as available to the outside world, so to speak. But if you have a lone pair, They're not distributed or shared among any other atoms other than nitrogen, so that makes their repelling force more strong than bonding electrons. And because of that, the remaining angles between bonding atoms decreases a little bit. So you may remember that the bond associated with the tetrahedral is 109.5, but if you have one lone pair, actually for each lone pair, the bond angle is going to get squeezed in or decrease by somewhere between 2 and 3 degrees. So if you have two lone pairs in a structure, for example, water, you're going to get an even larger decrease of the angle of remaining bonds. Double and triple bonds, understandably, also exert a stronger repelling force than just a single bond. And so in this particular compound where we have a double bond, it's going to push away, repel the two bonds around it a little bit stronger than a single bond would. And as a result, look at the distorted angles. The angle that has been squeezed in instead of being 120 is 111, and the outer angles that helped push are going to be greater than 120. I love the next couple slides. They're just a summary of all the possible electron geometry shapes depending on how many electron domains you have around a central atom. And then within each electron domain shape, it's also broken down into the molecular geometry depending on how many lone pairs you have. Okay? And so I think it'd be really worthwhile at least downloading this chart or Google another chart for electron domain shapes. Here's the rest of it. Okay. So again, if you have 5 domains and then varying number of lone pairs and then finally 6 domains. Alrighty. Now, it turns out most of the molecules in our world don't just have one central atom like this, okay? It's just very small molecules. But our world is made up of huge molecules. And so you might look at a structure like this and say, what? Wait a minute, where's the central atom? Which one am I supposed to analyze? Every atom along the backbone of a molecule should be analyzed individually by itself. Okay, what am I talking about? Well, let's start with the nitrogen on the end here. Go through the same procedure. How many electron domains? Well, you would have to know that there's a lone pair there. I better fill those in, huh? All right. So including that lone pair, there are 1, 2, 3, 4 domains. So that means the electron domain shape is tetrahedral, but this problem is probably asking for molecular shape. I think I didn't say that, but yeah, let's ask what the molecular shape is. So if you have a tetrahedral electron domain shape and 1 lone pair, the molecular shape is called trigonal pyramidal. Okay. Then you move on to the next atom. I'm just going to do this one because it looks interesting. So how many domains around this carbon? 1, 2, 3. Okay, so that means the electron domain geometry is trigonal planar. And it also means the molecular geometry is trigonal planar because there are no lone pairs around this carbon. And you need to find a way to be able to represent these shapes on paper. So chemists will use the following. You are probably not expected to be able to do that, at least till you practice. But chemists like what we call the wedge and dash shape. So a dash means that atom is going away from you, like into the board, into the paper. And this hydrogen is coming out at you. And that's designated with a wedge. Okay, so You can use that, or you can use the ball and stick method, which I think most of my students prefer. And you try to make it look three-dimensional by adjusting the lengths of the bonds. All right, so here's a summary of the two different 3D sketches that you should practice doing. One is the wedge and dash shape, and one is the ball and stick shape. That is it for this lecture.